Now, to understand between phylogenetic tree and tropical projective torus, we should know Plücker relation. So Plücker relation. But before to understand Plücker relation, we should know the concept of Plücker embedding. Because of lack of short of time, I cannot explain Plücker relation, but it is sufficient to introduce Plücker embedding. Based on the Plücker embedding, the Plücker relation in the concept of the algebraic geometry or granular basis is related to this. So I just explain the Plücker embedding. And to understand Plücker embedding, you should know the concept of Grassmannian. Grassmannian, the definition with Grassmannian is easy to understand. Denoted by G, R, K, N is the collection of K-planes in Rn, but K-planes erase the origin point. Okay. So that's notation NK. So substituting the concrete number, if n is equal to 2, that is plane, and K1 is a line. So this means that all collection of lines in plane. So this blue or this red line is a element of Grassmannian GR21. Okay. And then if K is 1, the GR31 means that naturally, obviously, a line, collection of a line in the space, you could R3. But the line must pass the origin point. Of course, this is origin point. If K is equal to 1, that is homeomorphic real projective plane. Okay. If K is varies like this, in the case the line is just to change a plane, but the plane also passes the origin point. In general, we can define G, R, and K. In that case, K, okay, is the relation is to define G, R, and K. The following relation must hold, and N allows not only the positive natural number, but also infinity. Okay. But when you consider Grassmannian, I explained the definition like this, but the set, as a set, the name is we can express the same set of Grassmannian by introducing a Stiepel manifold. So we can define this here as a set concretely as a set. One way is this, but the another way is to introducing Stiepel manifold and its equivalence class of Stiepel manifold. So that is process. We can define K prime and Fkn is collection of K prime. And give a relation like this. And we take the Stiepel manifold element, and if the equivalence the relation means that there exists a general linear map whose determinant is non-zero such that y is equal to ax. That is equivalent relation. We can consider a Stiepel equivalence class of a Stiepel manifold. It is equal to Grassmannian. So we can define Grassmannian defining a Stiepel manifold. One good point is that we can accept the definition. Grassmannian, we can check that Grassmannian is topological manifold. Because Stiepel manifold, that is manifold by definition of the manifold. And quotient map preserves, so that is also topological manifold. So, which means that is topological property, Hausdorff, and second countable basis, main topological property. And so we add some topological properties to as you want. Anyway, so then the additional topology property is so-called paracompact and T4 space and so on, okay? But anyway, the quotient map preserves the topological property. So in that Grassmannian, also Hausdorff and second countable basis, because quotient space preserves the topological property. So we can see Grassmannian is a topological manifold. Okay, if we accept the concept of the Grassmannian as a Stiepel manifold, we can see the following example. If if we choose the 2 by 4 matrix, in that case we can Stipple manifold F24, that is here. That is equivalent relation, because if we actually compute, we can find a matrix GL, in this case GL 2 4 GL 2R, sorry, GL2R. My lecture note is GR24, that is type 4. GL2R, 2 by 2 matrix whose determinant is non-zero, such that y is equal to ax. So that is equivalent relation. Next, consider a minor matrix like this. I will define 6 minor matrix: 1 2 1 3 1 4 2 3 2 4 3 4. How we can construct? 1 2 means that we can say that is 1 column, 2 3 4 column is given. 1 2 is, take this 1 1 1, sorry, that is 0. Okay, 0 1 1 0 1. 1 3 means that 1 0 1 2 1 0 1 3. Next, 1 1 1 2 1 1 1 3. Last, 1 2 1 3. If in this way we can take total 6 minor matrix. Okay, 6 minor matrix. And next, compute each determinant of the matrix. If we compute the determinant and enumerate these 6 coordinates, the first determinant is 1. Determinant of 1 2. 1 3 is 2, and that is 3. 1 2 1, and so on. So that is minor matrix 1 2 1 3. That is 2 4 3 4. In that, the bracket means that if we say as a bracket, this contained in P5 projective real plane space. Okay. So because this guys is equivalent, so X lives in GR24 as a equivalence. Okay. So we can construct this process means that we can construct a natural map or natural embedding from Grassmannian to P5. What about Y? If we compute in the same process, if we compute Y, this, we can obtain 3, 6, 9, 3, 6, 3. That is Y matrix. Find minor Y, 6 cases, and determinant each minor matrix. That is same as 1, 2, 3, 1, 2, 1. Because there exists, if we 3 times on given coordinate, we can make this value. And projective space, in the projective, real projective space, we can regard the point is same. Okay? That is definition of the projective plane. So 2 points, because 2 points lie in the same line, the point in a projective world, the 2 coordinate is same. Okay. Anyway, its equivalent class lives in Grassmannian. So we can construct a natural embedding from Grassmannian to projective plane P5. In general, that is, we can fix K is 2 and 4. We can fix the 2 natural number. In general case, there exists an embedding Grassmannian to nk minus 1. If in that case, k is equal to 2 and 4, you can compute 5, okay? So it is general. We can construct general map between Grassmannian and projective plane, and we call such an embedding a Plücker embedding. If we apply this concept to phylogenetic tree, as same n is equal to 4, k is 2. In that case, n means that total leaves is corresponded to total leaves in a phylogenetic tree, so like this. Okay. If the following phylogenetic tree is given, let's define a trimetry just we add the shortest path between each species or each leaves. For example, if 1 to 3, the shortest path is 1, 2, 3. Okay. So, based on the definition, if n is labeled with leaves, so we can take 1, 2, 1, 3, 3, 4. As you see, total 6 types of paths goes to 2 positive real number. In general, ij is given. That is the formula is explained the situation in a tropical geometry world. The multiplication is usual addition, and Pij means the unique path between leaves I and j just describe the path between them. Then we can, as you see, we can consider 6 vectors: 1, 2, 1, 3, 3, 4. As vectors, and we call the vector a cofinatic vector. So that is related to a Plücker embedding. The number of choice is 6, and in general, so based on the similarity between Plücker embedding and phylogenetic tree, n leaves of phylogenetic tree is given denoted by space. Then we can construct the following Plücker embedding. Grassmannian 2n 2 in that case, n is equal to 4 because 4 leaves. In this phylogenetic tree, we can construct Grassmannian between this, that is similar to that part. Okay. So anyway, the phylogenetic tree is related to Grassmannian and Plücker embedding. Based on this, the next topic I want to discuss is Plücker relation. And this by observing Plücker relation, we can see the relation between that and the tropical projective torus. So a phylogenetic tree is related to a tropical projective torus. But my main topic is on the translating P-Wasserstein metric into tropical language. I stop this topic and go ahead P-Wasserstein metric.